Ah, such a beautiful day, isn't it? It is, until it all goes boom. That's gravity disappearing for just a second. Let's recap the events from the smallest to the largest scale. We'll start with you. Yes, you. If gravity is lost for a single second, unfortunately, you'll most probably be no more. Thing is, gravity doesn't only keep you anchored to the Earth, it also holds all the atoms inside your body together. If this force completely disappears, even for such a short period of time, chances are you'll simply fly apart. Blah! If you don't, then you'll start floating above the ground. Not high though, because 1 second isn't enough to fly too far away. If the gravity stops working only for you, then you'll levitate a little over an inch upwards and then fall back without consequences. Your thoughts will be occupied by the lack of oxygen in your lungs though, because with no gravity, your blood will stop pumping. Now, if it affects the surrounding objects as well, you'll be lucky to be away from home because everything around you will float too. And after a second, all your cutlery, your bed, your wardrobes, etc. will smash down on the floor. Luckily, buildings and trees will probably stay put because they're strongly rooted in the ground by their own means. Still, the picture won't be pretty, and it'll be up to you to clean that mess. Ah, shucks. By the way, you surely know our planet is spinning and hurtling through space at mind-blowing speeds. So there's a chance that if gravity does turn off for a second, everything on the Earth's surface will succumb to inertia and fly horizontally at several hundred miles per hour. That will be an even bigger mess, but only if everything retains its mass. If it doesn't, then it should be no problem. Maybe. Yet, the real trouble starts if the gravity disappears for the entire planet. The force of gravity is equal to the pressure from inside the Earth, and if the outside pressure is gone, nothing will stop the molten innards of our planet from bursting onto the surface. An immense earthquake will begin all over the Earth as the tectonic plates move upwards. Also, all the world's volcanoes will probably erupt too, since the lava will be pumped up with the pressure. If such a mega eruption occurs, no life will survive except the sturdiest of creatures, such as tardigrades. The clouds of volcanic ash will spread across the whole planet, blocking the sun. At first, the temperatures will rise due to the greenhouse effect, but then the planet will cool down and a new ice age will begin. Optimistic. This will all happen even if the gravity returns after a second, because the motion will already start and it'll take a more powerful force to calm it down. Up above, the atmosphere of the Earth will simply evaporate. The air we breathe is also kept around the planet by the force of gravity, so if it pops, we'll have nothing to fill our lungs with. When the gravity comes back in a second, the atmosphere will eventually gather itself back, but the damage will have been done already. It will take a lot of time for the air to return to its original composition. Meanwhile, in space, things are even worse. As far as we know, everything in the universe is held together by gravity, including other planets, stars, galaxies, and even galactic clusters. On a cosmic scale, our planet is but a fleck of dust, having a really tiny mass. The Sun is incredibly huge by comparison. It's 109 times bigger in diameter and over 300,000 times more massive, which is why its gravity is able to keep so many planets in its orbit. And now that enormous force is just poof. Even though it's only a second, the immense pressure of gas from inside our star makes it explode, sending a heat wave far greater than anything we've ever experienced in history. Now, the Sun will most likely survive because a second is too short a period of time for the star to inflate too much. But the same can't be said about Mercury, Venus, Earth, and probably Mars too. Mercury, being the closest, will probably be simply incinerated. The temperature on Venus is already extremely high, but it will spike even more, scorching its surface. Good thing it's not inhabited. And bad thing that Earth is. The heat wave from the Sun will probably obliterate our atmosphere first and then do the same with the surface. So, from the looks of it, nothing will be able to survive again. Oh well. But that's not even close to the end. Our Sun is one of the smallest stars in the universe, the biggest known one being about 1,500 times larger and more massive. If such a giant loses its gravity for a second, everything around it for millions upon millions of miles will simply disintegrate, including other smaller stars. But the objects with the most mass and, as a result, the most gravity are neutron stars and black holes. Both of them are extremely small for their mass, like me. But the pressure inside them is so immense that the loss of gravity for even a fraction of a second might mean a tremendous space explosion. And with a whole second, it's basically warranted. Nobody knows for sure, though, how black holes operate, so there's a chance that something else will happen with them, or nothing at all. Finally, on the largest scale, if gravity decides to take a second-long break, surprisingly, nothing much will happen. Planets will mostly retain their orbits, although they might change a little bit, and if we talk about galaxies or galactic clusters, those won't even notice anything. The biggest changes will be local because, as I said earlier, stars will explode, and the larger the blast, the more it will affect the neighboring celestial bodies. For example, if a star large enough sends a wave of energy in the direction of our solar system, it might send asteroids flying toward us from the Oort cloud. Those space rocks fall onto the Moon and even Earth quite regularly, but they're mostly rather small. The ones sent to us by a star explosion, however, might be a lot bigger and more dangerous. We will be protected by other planets, but still, the chances of collision will be a lot higher than normal. But who cares really? We'll be toast by then. Obviously, this is all just speculation. Nobody knows for sure what will happen if gravity suddenly decides to stop working even for a second. What we know, though, is that it can't happen without numerous laws of physics being broken all at once. Scientists are pretty certain such a turning off is impossible altogether. For this to happen, everything in the universe will have to lose its mass first. Mass is the main reason things have gravity, so the heavier the object, the more gravity it has. Even you have it. It's just so small that you can't feel it. But if you were several million times more massive, you'd probably be the center of everyone's attention. Hey, I'd use that opportunity.
You decide to go out for a morning jog for the first time in your life. You put on your headphones and get ready for something hard and unpleasant. But as soon as you go outside, you feel an extraordinary lightness. At first, you enjoy it and speed up, but then you realize that something's wrong. You're running too fast and too easily. You feel like you've just taken off a heavy backpack that you've been carrying all your life. You're so fast, you think you must have a superpower now. But you notice another athlete running as quickly as you. You notice a puddle ahead of you and jump over it. You jump so far and so high, it feels physically impossible. You fall to the ground, shocked. Then you notice there are no scratches on your body, and the ground feels lighter. You stop the music in your headphones and turn on the radio. All the news reports say the gravity on the entire planet has decreased by half. Thanks to gravity, we stand on the ground and don't fly away into the sky. This power allows our planet to revolve around the sun and the moon to revolve around us. Heavy things seem heavy because of gravity. And now, something has happened to the Earth's core, and the mass of our planet has decreased. This is the reason for the change in gravity. People happily run out of their houses and jump twice as high and further than they used to. Any objects seem twice as light to you. Your body has become lighter, so you can easily stand on your hands. But still, you don't feel like a superhero. You can't lift a car, even if its weight was reduced by half. But now, parkour is easier for everyone than before. Your body's weight has decreased, which means you get less damage when you fall. However, panic quickly replaces the joy of the new conditions. It becomes hard for you to breathe, the same as all other people. The air has become lighter. The updated force of gravity has reduced the air pressure by half. Now you feel like you're at an altitude of 16,500 feet among the streets of a usual town. It's like you're halfway to the top of Mount Everest. The air is no longer as dense, and the main part of it has settled in the atmosphere. In the beginning, everyone experiences massive dizziness and panic. You feel like there's not enough air in your lungs, so you get nervous. To solve this problem, you have to learn to breathe slowly and evenly. Thanks to this, you calm down a bit. Others also learn to be more balanced and don't live in a hurry anymore. All of you experience less stress and enjoy every day. Then scientists create unique oxygen masks. You put it on, take a breath, and a special filter puts pressure on the oxygen molecules, making the air denser. After a couple of decades, people will take off these masks as they'll ultimately get used to the new conditions. New generations will be born with adapted lungs. The Earth's atmosphere is expanding. It seems the sky has risen higher and acquired a darkish hue. Satellites flying around the Earth's orbit are now inside our atmosphere, but the Earth's gravity still attracts them. You see thousands of satellites burning up. Some of the space debris survives the atmospheric shield and falls to the ground. A meteor shower begins. Space trash crashes into houses, roads, trees, and cars. You and the rest of the people decide to wait out the storm underground, in the subway or basements. Fortunately, the shower doesn't last long. People come out of their hiding and look at the sky in surprise. The moon changes its previous position and slowly flies away. Soon it disappears completely. Our planet is now like a heavy ball in the center of a huge blanket. That blanket is gravity. It bends under the ball's weight. If you put any light object on the blanket, it will roll down to Earth. But if an object is moving at high speed, it will be able to spin on the blanket's edge and not fall into the center. Thanks to such speed, the moon doesn't fall on us, but at the same time, it can't fly away. Now that gravity has decreased, the blanket has become twice as loose. The rotation speed allows the moon to fly out of our gravitational field. It just goes into space. People will be able to observe the wandering moon for a long time through telescopes. Meteorites might crash into it. It could also find another planet with stronger gravity and will revolve around this new home. The moon may stay in place, but will be revolving around the Earth at a slower speed. In any case, there will be no more tides on our planet, and the sea level will remain the same. In the sea, you can also feel the changes. It's much easier for you to stay on the water, and you can swim faster. But the coolest thing is running along the shore. The splashes are floating in different directions, so slowly and beautifully. The waves are running on the sand in slow motion too. The weight of cars, planes, and ships has reduced, and so people consume less gas now. You can drive twice as far with a full tank. Fuel transportation is easier, and less energy is spent on flights. Gasoline is becoming cheaper. The decrease in gravity inspires space tourism development. It becomes much easier for people to fly out of the Earth's orbit. Winter has come. You're walking down the street during a snowfall. It seems to you the snowflakes are stuck in the air as they're so slow. You step on the ice and realize that it's almost impossible to walk on such a slippery surface. Your weight has decreased, and the pressure of your feet on the ice is twice as weak. You're sliding and can't stop. You often fall, but you don't feel any harm. When the wind is strong, it's hard to stay on your feet. If you jump, you may even fly away. The grip of wheels on the road deteriorates. A driver can no longer brake abruptly. The wheels don't spin, but the car continues to slide for a while. That's why new speed limits are being introduced all over the world. You can still enjoy extraordinary strength and long jumps, but after a few generations, the human body will evolve and fully adapt to these conditions. People and animals will be born taller and bulkier. Majestic tigers the size of a truck are walking through the city streets. Flamingos the size of a plane are flying in the dark blue sky. But the worst thing is that the size of insects has increased too. A regular cockroach can now grow to be the size of a computer mouse, and tarantulas become twice the size of an adult palm. At the same time, all living beings become lighter in weight. Humans will become elegant and agile creatures. Our bones and muscles will stretch. The structure of the entire human body will change. We'll become thinner and smoother. Blood in the veins and vessels will flow more slowly, and it will greatly impair the brain's work, but only in the beginning. In the future, the body will expand, the brain will increase, as will the number of neural connections inside. The lungs will become more sensitive and spacious. People will be smarter and wiser. All devices and materials will be developed according to the new conditions. A cup, a pencil, a plate, phones, and other gadgets. Everything will get lighter and more fragile. If an ordinary person gets into such a world, they'll feel like a superhero. You'll be able to punch through lightweight walls and doors and break bricks with your hand. New people won't match your power, but you'll seem too small and clumsy to them.
Legend has it that in the 17th century, Sir Isaac Newton noticed an apple fall from a tree and began wondering why the fruit had fallen to the ground and not upward or sideways. Well, that would be freaky. After years of studying, he concluded that gravity must be the culprit. The scientists called it a force of attraction that existed between all objects. But it was Albert Einstein, many years later, that revolutionized these ideas about gravity. Legend also has it that he wasn't completely satisfied with Newton's findings. Something just didn't seem right. As a young scientist, Einstein had some trouble formulating his theories, trying to explain the behavior of moving objects. When an experiment came to his mind, he called it the happiest of thoughts. Gravity feels like the sensation of riding in an ascending elevator. He called it general relativity. Einstein began working tirelessly, trying to prove this idea. At one point, he even complained he was on the brink of losing his mind. Now, in the simplest terms, general relativity claims that gravity is the curvature or warping of space. The greater mass an object has, the more it warps the space around it. Imagine a heavy ball resting on a trampoline. The rubber sheet under it gets warped under its weight. It's the same with our sun. It's big enough to twist space across the entire solar system. That's why our planet, as well as all the others, orbit around the star. This warping also impacts how we measure time. If you look at your watch, time seems to go by at the same rate every day. But if you hike to the top of a mountain and your friend wanders through a valley at the bottom of this mountain, you'll see that your watches will calculate time differently. One watch will tick faster, while the hands of the second one, which is traveling through the valley, will move more slowly. That's because gravity affects how fast time goes by. With these experiments in mind, Einstein concluded that gravity was not a force of attraction, but rather a curvature in the fabric of space-time. We feel gravity as a force simply because we're placed on some surface. If there was no surface and no attraction between us and this surface, we would become weightless. If you don't mind getting some weird looks, try this experiment. You'll need a bathroom scale and an elevator to ride. You'll soon see that your weight fluctuates as you move up and down in the building in the elevator. The gravitational force is the same, but your weight is different because the elevator speeds up and slows down. Aboard the International Space Station, astronauts literally move along with the station, so there's nothing to push them against the side of the station so that they have some weight. Even if we still think of gravity as a force, it's the weakest one we know. First of all, it only attracts. There's no negative counterpart that could push things away. And weirdly, even though this force is strong enough to keep galaxies together, we still overcome it every day. Every time you lift an object off the floor, you overcome the force of gravity produced by the entire Earth. Ooh! Just to paint a better picture, Earth's gravitational pull is weaker than the power of a refrigerator magnet. The fact that our planet has gravity also affects the way we look and act. All creatures on Earth are limited in growth by the height of their skeleton and by how much weight it can carry, which is directly proportional to gravity. That's why some marine creatures can grow bigger. The largest animal on our planet right now is the Antarctic blue whale. It's about the size of 2 school buses combined. That's because sea creatures can float, which slightly counteracts gravity. The effects of gravity can be seen in people, too. We are taller in the morning than we are in the evening. Our everyday activities and the added effect of gravity make the cartilage in our ankles, knees, hips, back, and neck compress. Once you have overnight rest, the cartilage swells back to normal. Gravity might also affect your shower routine. That is, if you're an astronaut. They have to rely on the old-fashioned way of bathing up there on the space station. They can't take a shower since the force of gravity up there is different and water doesn't flow as it should. Instead, they use liquid soap, water, and no-rinse shampoo. They first squeeze some liquid soap and water from pre-made water pouches onto their skin. Next, they open the no-rinse shampoo and add a little water to wash their hair. Towels are then used to wipe off the excess water, which is really precious in space. To make sure they recycle it, an airflow system quickly evaporates excess water. Gravity and weight shouldn't be confused. Astronauts on the space station do float, and you may sometimes hear that they are in the state of zero gravity. It's far from the truth, though, since gravity up there is about 90% of its value on our planet. But astronauts look and feel weightless, since weight is the force a certain object exerts on them back on Earth. Most creatures have evolved to sense and adapt to Earth's gravitational pull. In the sea, for instance, some fish have floating calcium carbonate deposits in their heads. Scientists call them ear stones, and they're pulled down by gravity. They act like a fish's internal compass. Now, plants have evolved to grow starch grains in the tips of their roots. They use this amazing feature to force their roots deep down into the soil. As little as we seem to understand it these days, we do need gravity for way more things than we can imagine. For instance, some bacteria become even more dangerous in space where there's little to no gravity. Salmonella, for example, the type of bacteria that is known to cause food poisoning, becomes 3 times nastier in the condition of microgravity. So you really gotta cook your chicken. Our own moon stays where it is because of the effects of gravity, too. If it weren't for this force, our satellite would have floated away by now. But it's held in place by Earth's gravitational pull. Objects with the biggest gravitational pulls in the universe are black holes. Thankfully, our planet is really far away from any of them. Nothing can escape the gravitational pull of a black hole, not even light itself. Similarly, gravity is different on each planet, and because of that, things weigh differently depending on which planet they're on. Take Earth, for example. An object that weighs 100 pounds here would only be 38 pounds on Mercury. But if you're planning on losing weight fast, try booking a trip to Pluto. Someone who weighs 150 pounds on Earth would weigh no more than 10 pounds on Pluto. The same person would weigh considerably more on Jupiter, which is the planet with the most powerful gravity. 150 pounds on Earth would turn into more than 354 pounds there. No thanks. Remember that experiment with watches ticking at different levels of elevation? It turns out that gravity isn't spread evenly on the surface of Earth. Why? Because our planet isn't a perfect sphere. The mass of Earth isn't evenly distributed either. That's why you get variations in gravity in different locations. More so, gravity is weaker at the equator because of the centrifugal forces produced by the planet's rotation. Since we've always perceived gravity as a force, we seem to believe that it has somewhat of a suction motion. But it's not exactly true. Back in 1998, scientists were baffled to see that the expansion of the universe was speeding up. So they linked this to the repulsive gravity of mysterious dark energy. We now know that dark energy makes up for more than 60% of the mass energy of our whole universe. But since nobody knows what it actually is, we can only make assumptions. And one that's largely accepted is quantum theory, which seems to claim that gravity pushes rather than pulls things in. You got all that? I may need to watch this one again.